The solar cycle. Historically, as people have observed the sun, they've noticed a variety of things. One of the things they noticed is that the number of sunspots changes fairly regularly. And it follows a cycle where there are times when there are a lot of sunspots and times when there are not very many at all. The other thing that they've noticed is that the sunspots that we can see on the sun from day to day indicate that different parts of the sun rotate at different rates, and we call that differential rotation. And in particular, as we see in the illustration here, sunspots near the equator of the sun move very fast. Sunspots near the poles move very slow. And it turns out that these two observations are connected. The reason that the number of sunspots change, and even why there are sunspots at all, is very much linked to the fact that the sun does not rotate as a solid body. The sun is gaseous. And this kind of rotation is actually very typical of gaseous bodies. We also see it in the gas planets. The Jovian planets, Jupiter, Saturn, Uranus, and Neptune, also rotate faster at the equator and slower at the pole. So how does that tie in to how sunspots form? Well, the sun has a magnetic field. And here we see the magnetic field lines. Now these would actually extend out into space and connect back in. So the sun is like a giant magnet. And so we can picture magnetic field lines very much like a typical bar magnet. So here's our imaginary bar magnet with a north magnetic pole and a south magnetic pole. But we said that the sun rotates faster at the equator than it does at the pole, this differential rotation. So that is going to affect the magnetic field. And that's what we see in this second image, that the magnetic field at the equator is getting pulled around faster than the magnetic field at the poles. The effect is that it's going to be stretching the magnetic field. So lines that were nice and neat and straight have now become very stretched and distorted. When it gets very distorted, that's when we get the formation of kinks. Now these kinks are what we see as prominences. So that same little loop of material that we saw as a prominence in the chromosphere is directly linked to this stretching of the magnetic field. So we've got these little kinks. The base of the kink is where we're getting the sunspot, because what's happening is that the magnetic field holds in the heat. So it's preventing the heat from the sun's interior from reaching the surface. And so it's making that little spot cooler. And of course, when things are cooler, it's going to look darker. The sunspots, as you can see on this graphic, the temperature of the sunspots isn't cold by any stretch of the imagination, about 4,500 degrees Kelvin. That's about 9,000 degrees Fahrenheit. If you could somehow scoop up a sunspot and take it away from the sun, it would be a very, very bright object in our night sky. So it's really just the contrast, the fact that the surrounding part of the surface is so much hotter, it's going to look much brighter, and these are going to look very dark. So here we see a contrast. All of these white spots that we see here are places where the magnetic field is distorted. So this image is solar maximum. So during solar maximum, you're going to have lots of sunspots. Let me change color here. Lots of prominences, because you have lots of kinks, and both of those require the kinks. More prominences you have, the more the kinks break. That's going to give you solar flares and coronal mass ejections. So all of these are associated with the magnetic field kink. So the more kinks you got, the more sunspots you got, the more prominences you got, the more solar flares you got, the more coronal mass ejections you've got. Now eventually, the lines get wrapped around so many times that you get lines pointed in opposite directions side by side. And when they are like that, that's when they're going to start to cancel out. So up to this point, you're getting more and more sunspots, but then it starts to cancel out. And so now everything is going to decrease in number. So we're going to be seeing fewer and fewer sunspots, fewer and fewer prominences, fewer solar flares, fewer coronal mass ejections, until we're back to our undistorted magnetic field. And when the magnetic field is undistorted, that is solar minimum. Whoops. Minimum. Anyway, you know what my word is there. So now we're going to see very few sunspots, very few prominences, solar flares, or coronal mass ejections, because now there aren't many kinks. So as the sun goes through this cycle, we'll every time see all of these things increase in frequency and then decrease in frequency. And that's what this is a graph of. This is a graph of number of sunspots per year. And you see that for the most part, it's fairly regular. Number of sunspots increase, decrease, increase, decrease, increase, decrease. So we're seeing solar max and solar min. And roughly every 11 years, from maximum to maximum, it's also roughly that amount of time from minimum to minimum. But it's not perfect. Sometimes it's 9 years, sometimes it's 13 years. But on average, it's an 11-year cycle. Notice this period of time right in here. That was back in the 1700s, late 1600s, early 1700s. Almost no sunspots. which means almost no prominences or any of the other stuff. This also happened to correspond with a period of time known as the Little Ice Age. So this has many people wondering what is the connection between the solar cycle and our climate. Obviously, when the sun is inactive, it has reduced our temperature, but we don't fully understand what that connection is. So, interesting thing to study, but something that is not fully understood. Thankfully, our sun is fairly regular about going through this cycle, and so for the most part we do not see major climate effects from our sun and the solar cycle.